Answer the question over here.
Oh, yeah, over there.
Thanks.
Well, welcome everybody. Today I am pleased to introduce you Francesco Costa. He's a PhD student at University of Göttingen, working with Laura Covey and with one of my most favorite physicists of all time, Steve King. Yeah, he's going to be talking about freezing, which is the topic of his PhD thesis. Yeah, the floor is all yours.
Thank you very much. Thank you for having me here and to be here to listen to this talk. So yeah, I want to discuss a little bit freezing, some problems in this dark matter production mechanism, and maybe some opportunities that we can find. So the outline of the talk will be an introduction on the difference between freeze-in and freeze-out, and then a bit of a discussion on the problems of freeze-in, and see what solution we can find, and then we will see what happens when we study low reheating temperatures to our production mechanisms. So one disclaimer. So what I will show at the end about low reheating temperature, that's actually applies to general models. It doesn't need to be what I will discuss, so scalar dark matter. I'm just discussing that because it's the easiest model to have a look at and to understand what's going on. And then I will assume during the talk that dark matter exists and it's a particle. So these are basic assumptions that I will do throughout the whole talk. Okay, so let's go with the introduction. So probably you know already, you're familiar with the freeze out, but just to review it a little bit, this is the, if you want, the standard production mechanism for dark matter. And what happens is that the dark matter in the early universe, so in this part of the plot, so in this axis we have the mass of the dark matter over the temperature. So the evolution of the universe goes this way. So in the early universe here, the dark matter is in thermal equilibrium with the standard model. So it doesn't really matter what happened before, if the dark matter was produced through the inflaton or whatever, because it thermalizes and then it follows the Fermat distribution, so which is this black curve here. Then at some point, when the interaction rate that I'm calling gamma here becomes on the same size as the Hubble rate, then we have what is called freeze out. So what happens is that the dark matter goes out of equilibrium and then the number density freezes. So we get that number density today. That's how the dark matter ends up to be what we see today. The stronger the interaction, the longer the dark matter remains along this thermal equilibrium curves, so the less abundance we have today. Yeah, so this is the co-moving number density on the y-axis. And the basic features are, as I was saying, there is no dependence on the initial condition. The couplings that we need to get the correct rate abundance normally are of the order of the weak force coupling. Yeah, so around 10 to the minus 2. Okay, the problem with the freeze out, if you want, is that loads of vanilla freeze out models, which are called WIMP, are very constrained or excluded. So this, for example, is a scalar Higgs boson. This is the Lagrangian term that we have. We have a scalar dark matter S squared, and it couples with the Higgs, and this is the process.
Just before,
sure.
Supposing the only interaction that the dark matter had was gravitational, when would freeze out happen in your graph? When do the gravitons decouple?
Right.
From the dark matter.
So if I may,
yeah,
if you're assuming that the only interaction dark matter has with anything else gravitational, then the assumption is that it was also produced separately from the standard model particles. So
yes.
we had decoupled before.
Exactly.
For example, in the cases of dark matter kind of coupling to inflaton, for example, then it would be produced independently during reheating after the end of inflation.
I guess probably it wouldn't thermalize because the coupling is too small.
Yeah,
Yeah.
exactly. That's what I'm expecting. It doesn't thermalize.
Yeah,
So it's an assumption that it thermalizes.
exactly. Yeah.
Dark matter will always couple to gravity.
Yeah.
Kinetic energy job. There's
Yeah.
no way to
Definitely.
switch it off.
Yes, but does it thermalize is the question.
That's a different issue. No?
That was the real question. When does it thermalize? What temperature will it thermalize? And the answer presumably is it probably doesn't thermalize.
Yeah, coupling is too small. Yeah. I will actually discuss some production through gravity in a second. But yeah, so if you want a WIMP, generally you need to introduce some extra coupling to the standard model. So in this case, for example, this one for the scalar. So in this plot, you can see on the y-axis we have this lambda. So in this paper it was called lambda x, and then the mass of the dark matter. And this red curve is what is constrained by the Planck measurement. So this gives the correct relative abundance for the dark matter. And as you can see, it's pretty well constrained. So here we have the branching ratio of the Higgs into invisible. So constraint coming from accelerators, and these are direct detection experiments. And nowadays we are at LZ, so practically here. So just the tip of this resonance is still allowed. And this, I mean, I'm not saying all the WIMP dark matter candidates are excluded, but the simple ones are very much constrained. Also because these direct detection experiments were built exactly to find a WIMP path.
The white region is the only one that's allowed, is that correct?
Yeah, exactly. And then in the future, there are plans for other experiments that will bring a little bit down this curve. That's the reason that brought people to try to explore other production mechanisms or other candidates like the action. But here we're going to discuss the freezing, which you can imagine it as a production mechanism in the other side of the spectrum with respect to freeze out. So here we never equilibrate the dark matter with the standard model. And therefore we get a dependence on the initial condition. And we need to assume that initially we have a negligible abundance. Because, so if you imagine you get loads of production through the inflaton or something like that, it never thermalizes, so the number density remains until today. So if on top of that you get some freezing, you might just overproduce. So normally it's assumed a negligible initial abundance. And if you go on and do your computation, you see that the coupling that you need in this case are very low, order 10 to the minus 10. And yeah, so with out of equilibrium, generally, but we'll see it a little bit better. That's why I put the asterisk there. We'll see it a bit better later. We can imagine that the production rate is smaller than the Hubble rate throughout the whole evolution of the universe. And in this case, if you want the yield, which is the number density over the entropy density, or the final relative abundance at the end, is it goes like the coupling square. So the stronger the coupling, the more dark matter you produce, which is the other way around with respect to the phase out. Nice. And we can represent this into this simplified plot if you want. We have the relative abundance on the y-axis and the coupling on the x. So freeze out stays around coupling order 1, and you increase the coupling, you get less dark matter. With freezing, it's the other way around. Coupling very small, and increasing the coupling, you increase the dark matter production. And as you can see, there is this region in between where both production just lead to too much dark matter. So there, none of the two production mechanisms actually work because they overproduce. Right.
So
So
can you go back 2 slides?
yeah.
You had these curly lines referring to that one.
Yeah.
So in freezing, the abundance is proportional to coupling squared. In freeze out, it's not over lambda squared.
Yeah.
Yeah, that's a very good distinction.
Yeah, good. Right, so now I want to just show you quickly what happens when you do a freezing computation, just to have a feeling of what we do normally. So here we have the Boltzmann equation. So this is the evolution of the number density, so the derivative of the number density. Then here we get a term just that depletes the number density just because of the expansion of the universe, and this is our particle physics. So we have, in this case, we are still in the Higgs quantum. We have two Higgses going into the scalar, so producing more scalars, and the annihilation of the scalars into the Higgses. And these terms, this goes like the number density of the Higgs squared, and this like the number density of the scalar dark matter squared. And we can call this the forward process, and this the back reaction. The nice thing about freezing is that you can completely remove this term, because this goes the number density squared, and as we said, we need to assume negligible initial abundance. So we can neglect this term in our computation. So
just to clarify, you're assuming pairwise annihilation, but the only vertex is pairwise, or pairwise production and pairwise annihilation.
Yeah.
You get a different power if you assumed it was 3-to-1 or 1-to-3 or something.
Yeah, I think then you get a different power in n, but those processes are normally suppressed.
Well, usually in the Higgs boson model, you impose a Z2 symmetry under which your dark matter is odd, because you don't want your dark matter to decay, because that's bad. Well, you do have decaying dark matter models, but then the decay rate has to be slower than the age of the universe. So usually you kind of stabilize the dark matter from decaying, so you only see pair annihilations. And yeah, the production as well comes to pair because of the Z2 symmetry.
But it could be triplet annihilation.
Triplet annihilation, you mean?
3-to-1.
Why
does it have to be 2?
3-to-1, yeah, so that would be allowed as well, but because, you need more 3 dark matter particles to come together.
Yes, that's going to be very rare.
Yeah.
It's going to be very stable then.
No, definitely it will be. Number changing processes that, as he said, would be kind of suppressed. But there are models like cannibal dark matter, which have very strong self interactions, which do that.
Similar question. Is this assuming the number of particles is the same as the number of particles?
Yeah, so actually, so in this case it's just a scalar dark matter, then yeah.
So this is the simplest model situation.
Yeah, exactly. So yeah, we choose to study the scalar because very simple and can bring on and also some of the aspect that I will discuss a bit later just apply to scalars. We're also studying like a spin 3/2 dark matter where the story is a bit different. But yeah.
May I add,
sure.
Those semi-annihilations also pose a lot of trouble because then you still have to agree with observational data. Whereas in the center of galaxy where there's a lot of dark matter, those kind of strong semi-annihilations or cannibal processes would not violate, but they'd be in tension with structure formation bounds.
Most intergalaxies have very large black holes, so I'm not quite sure why.
Well, if you have a large density of dark matter and you allow for those self-interactions, then if the number density changes, then you have to somehow release the energy.
It would still be very rare though if it's 3+1.
Definitely it would be very rare. But what I'm saying, in models that allow for such strong couplings, I think there are since strongly interacting massive particles, then you do have those kind of constraints that you need to worry about.
Yes, I mean, surely if the strength of the coupling is strong, then you have a very different scenario.
Absolutely. No, that's not what he's studying.
Yeah. Okay. I thought he was in the weak coupling.
Yeah. Right. So practically, we just need to study this production rate here, which is quite simple at the end. It's just an integral in the center of mass energy, S. because you can rewrite this integral, 6-dimensional integral, into just one integral in the center of mass energy. Is quite convenient parameterization that was done back in the day. Yeah, and if you go on and do that integration, approximate it, then, for example, your dark matter mass is much bigger than the Higgs mass, then it's just one line in Mathematica, you can plug it in, and you get a Bessel function with the mass of the scalar over the temperature. So if you want here, we can see already how this, this production rate goes. This is the temperature that decreases, and you see if here I set the dark matter mass to be around 100, after 100 this production rate goes down quite fast. So around the mass of the dark matter, my production practically stops. And once I know this gamma, I can just integrate my Boltzmann equation to the temperature and find the final result for the number density or the radic density. So I integrate from 0 to infinity, also an approximation. This should be the highest temperature we can reach, and this should be the temperature today, but it's a good approximation in this case, also because this function inside, as we saw, is just killed after the temperature goes lower than the mass of the dark matter. So finally, we get this radic density. You see, we have the Planck mass. It comes from Humboldt, and then we have this ratio between the critical energy density and the entropy density today. But most importantly, we have this dependence on the coupling squared. And since here we have the Planck mass, yeah.
What is the right-hand side of this equation? It's a prop.
This one.
See, the right-hand side is integrated over t, so I'm not sure what the symbol is telling me. Are you telling me that n is proportional to this?
All right. Yeah, this should have been like an arrow, probably. Right?
For what symbol? What is?
Yeah, for n.
N
Like,
is proportional.
yeah, yeah.
What is K1?
Sorry?
K1.
K1 is the Bessel function. The Bessel function.
Bessel function.
Yeah. Yeah. Yeah, so practically from here you can see already why this lambda needs to be 10 to the minus 10. So, yeah.
Where did the Planck mass come from?
The Planck mass comes from the Hubble.
What's that got to do with the Planck mass?
Sorry?
What does the Hubble constant got to do with Planck mass? It's just the expansion rate.
Yeah.
That doesn't go for gravity.
No, it does. Well, you write the Hubble rate in terms of either temperature or the Planck mass.
Like you can write it in terms of the Newton constant or the Planck mass. Like you have t squared and then some constant in front, right? And there it comes.
Oh, you're shooting photon. Yeah, just from photon density.
Yeah, so here we are in the
So the
radiation domination.
H bar in the matter, not the gravity.
Sorry?
The H bar is in the matter, not the gravity.
Yeah.
It's nothing to do with quantum gravity.
No.
Okay, cool. Another possibility is if you study non-normalizable couplings, where your matrix element squared, or if you want your cross-section grows with energy, then you have a bit of a different behavior. So since the cross-section grows with energy now, you have most of the production at the highest energy, so the highest temperature. So assuming instantaneous reheating, then at the reheating temperature. So then at this point, your your omega is squared, your radic density also depends on the reheating temperature. So here you can see the blue curve has a bump at the reheating temperature and then pretty much remain constant. Right. Okay, so this is the general picture of freezing, but we have some problems. So first of all, we have these tiny couplings, which can be technically natural if they don't run that much due to RG running. But at the same time, you need to accept to have this tiny coupling in your Lagrangian as an assumption, and plus makes everything very hard to observe.
Right. These tiny couplings are just for the scalars.
It's general for freezing.
Because if I went back and I discussed fermions, for instance, I presumably would have had a Yukawa coupling, which would have had something like HH goes to, not even HH, I'd have something going to the dark matter candidate from two fermions.
Yeah.
Will that give me an n squared? Or that will give me a linear in n, so things would change, and the coupling presumably is allowed to be much larger.
Let me think. So if you have a fermion dark matter, still you need like psi bar, and then so if you want to couple with the Higgs, then you have H dagger H psi bar.
I mean, if the dark matter is still boson and is created by two fermions, that's a Yukawa.
Well, it wouldn't. So it's Higgs boson, right? So
Sorry,
it's a Higgs boson model. So the only way dark matter talks to the standard model is through the Higgs. So for two fermions to go.
Oh, you see, he has assumed a very particular model here.
Yeah,
I didn't see any model.
Yeah, well, the Higgs boson coupling that he showed, that the lambda HS that sits in front of a square.
I thought that was just one example that he was.
Yeah. So I mean, in general, for freezing, you don't go much higher than 10 to the minus 8 or 10 to the minus 7.
Any known processes in any of the candidate models for dark matter.
Well, I mean, I don't know if I can be so general, but the one I've seen also, because otherwise you thermalize if the coupling becomes 10 to the minus 4 or something like that. You start thermalizing. But yeah, from my knowledge, the different portals that you can have, so through the X or through neutrinos or whatever, you always get coupling of this size. 10 to the minus 7 maybe is the highest I've seen.
Your focus is on a particular Higgs portal model, and that require this 4 vertex, this 2 Higgs to do. Yes, that's essentially you're sticking to that particular thing.
But I think even if you don't get that, say you have a IS channel or something, then you still get like Yukawa squared, and then Yukawa squared and mass, Planck mass, and then you get similar order of magnitude. Yeah, but here we're just looking at the Higgs portal because it's, I think probably the easiest way. Right. The other problem is that we can actually have production due to gravitational coupling of the dark matter. And in freezing, all of this production is not washed out by the thermalization. So if you produce something, that will stay around. So if you want the simple picture, is that at the end of inflation, we have the inflaton oscillating around the minima, and this in turn make the scale factor to also oscillate. We can write it in this way, where we have an average part which decreases with time, so the oscillation gets smaller, and then we have a part which depends on the inflaton that I call phi. So then we have an oscillating background metric, and this leads to particle production.
So it's different from the resonant production from inflaton. It's actually coming from the metric?
Yes, so I'll show later also the results from production during inflation. This one is production during at the end of inflation, so when the inflaton starts to oscillate. So
the oscillation of the metric transfers into the resonant production at reheating.
Yeah, practically the oscillation of the inflaton makes the scale factor oscillate, and that leads to particle production. Practically, we can see, I think this is the clearest way for me to understand it. So if you write the action for your scalar S, and here you have G, and you plug in an oscillating A scale factor, then you can see that practically you have a coupling between S and the inflaton through gravity pretty much. Because you plug in G mu nu in here, and then since A depends on phi now, then you have a sort of effective coupling between the inflaton and the scalar.
So is that action, is that in the Jordan frame or the Einstein frame? I'm guessing it's in the Einstein frame because you don't have the non-minimal coupling to gravity, which is how I would understand the inflaton coupling to S.
Right, but so you don't need to write any non-minimal coupling to gravity to have a coupling with the inflaton, if you want, in this case.
In
So,
the Einstein frame, that would be the case.
yeah, I have to say I'm not 100% sure.
So the Einstein frame usually refers to the dilaton. You're assuming a dilaton as the inflaton.
Well, I don't know about the dilaton, but I guess it would be a dilaton, yeah. But the way I understand inflation is that you start from the Jordan frame where the inflaton and the non-minimal coupling.
It's just a standard scalar field.
Yeah.
The non-minimal coupling x c times the curvature y squared.
Yeah. Whereas when you write it in the Einstein frame, then
That is the Einstein frame, usually. I would have said. Because it's the square root of g times r. And you've got a scalar field.
No, you go from the Jordan frame to the Einstein frame. In the Einstein frame, you don't see the non-minimal coupling explicitly.
You can do a conformal transformation to it. But I would have said that the first one was the Einstein frame because that's the physical. You're assuming that's to be the physical metric.
Okay, well then maybe I've got them the other way around. So you write in the Einstein frame, the non-minimal coupling is explicit, whereas when you go, if you do the conformal transformation.
Yes, it's not. It's no longer. It should be no longer because the other matter is coupled to G mu nu. It's not coupled to. It's coupled to the Einstein gravity.
Yes.
And if you're going to go and assume that you're going to get a dilaton or a scalar field that's the inflaton, you can do a conformal transformation to it and write it in terms of phi some power of some scalar times the metric, but that's going to reappear in other fields.
Of course,
Maybe that's what he's done. I was wondering where the phi came from here.
Yeah. So my understanding of this is that right, once we can write the scale factor as dependent on phi the inflaton, then then we have the metric, which is this one. Then if we plug in the metric here and here, then we get an effective coupling between phi and S.
So that's.
I think another way of asking the same question is, how do you add the outside scale of gravity?
Exactly.
Is it just R, or is it a function of phi times R?
It's
That's the same question.
It's square root of g times r.
That's what I would have thought.
I
would call that.
His explanation doesn't know where it comes from, but it's just square root of g times r.
Okay.
I'm sorry, can I ask, what is little n?
Sorry.
Little n in your form?
Good question. What is this?
N?
Yeah.
Oh, this N. Oh, yeah, sorry. This is the potential. So the potential for the inflaton would be phi to the n. So like a generic,
potential.
just a generic, generic potential. Yeah. Right. So then, I mean, people did this computation, both like recently, but also like I think it's a known thing. That we have this particle production, and you can go on and compute again this production rate for your dark matter, and you can compare it with the Planck results, and you can get a bound of the mass of the scalar particle, which is something like this, which it practically depends only of the scale of the end of inflation. And you can see if we plug in 10 to the 14, the mass is already constrained to be lower than some GeV. And this is independent on the quality coupling, so the self-coupling of the dark matter, as long as it's not too big and then thermalizes the dark matter. So this is already quite problematic in the sense that most models look at mass of the dark matter, which are in the order of GeV, some TeV, and we can see already that with this simple production in the very early universe, those models would be already not valid. So the assumption that the dark matter initial abundance is negligible is not actually valid. So we thought, how can we rescue 3Z, if you want, in case we have loads of production in the early universe. And one of the way one can do that is having an early matter-dominated period between the inflation and the radiation-dominated epoch. So if you want this matter-dominated epoch, can be done just by the inflaton that keeps oscillating around the minima, and the decay into the standard model particle is very, very slow. And we can parameterize the length of this period by delta NR. Which is pretty much the length of this matter-dominated period. And what we can do is then translate the bound that I showed you before in the mass into a bound instead on this length. So given the Planck constraint, we know that this needs to be bigger than 10 to the 6 in these units in order not to violate the observation. So practically we get a lower bound on the length of this early matter-dominated epoch.
Sorry, delta NR which I mentioned was.
Yeah.
And what was it characterizing that time? This length, is this the time interval?
I mean, in the length in the sense, like the ratio between the elbow at the end of inflation and the elbow at the radiation domination. Yeah, it's not
the ratio, okay.
Yeah,
Not
yeah.
after time.
Yeah, it's not time, it's not time. Yeah. Right, and to understand the dilution, right. So what happens is that if we produce something in early time through the inflaton and so on, then we have this early matter-dominated period, and we can dilute away some of the production. And this happens, that we can see how this happens. So in standard cosmology, we can say we have the inflaton here, then we have instantaneous reheating at the end of inflation, which I call Tn. And then I want to see the number density, what it looks like at some late time t. So in radiation domination, we have the scale factor that goes like this. And then I can just plug it in the number density. So the number density scale like a to the minus 3, and then this would be what it looks like, the number density at some late time small t.
So the problem was that you produce too much dark matter, you want to dilute it.
Yeah, I want to dilute it, yeah. And this would be in the standard cosmology, and if we have early matter-dominated epoch, then let's say that the matter-dominated epoch ends at this t. So in this time, the scale factor goes like 2/3, and so this is what the number density would look like at some late time t. And if I take the ratio, I can see that this is, if I take the ratio between the n in a non-standard universe and n in the standard universe, then this is suppressed depending how far I put this late time t, where the matter-dominated period ends. And that's why one can see that we get this suppression of the number density, so a dilution of the amount of particle that I produce during inflation. So this is the final picture. We can have a very small coupling between the inflaton and the standard model, so that the inflaton can oscillate for a long time and create this matter-dominated epoch. And then we have this delta NR that gives me it tells me how big or like how big is the ratio between the end of inflation and where my actual reheating happens. So when the inflaton decays and create the thermal bath.
So in the beginning, when you were motivating this, you said one of the issues with freezing is that the coupling is so small that you can't experimentally access the model. So is that, so you're still assuming, I guess, a freeze-in production or coupling type thing to some extent, but your coupling is too large, you produce too much dark matter, you want to dilute it, but which is good, you get the correct value density, but you want the coupling still be of a reasonable size so you could access it experimentally?
Yeah, so in the sense that, so the production that I was discussing here, gravitational, is, I mean, you could call it freezing, but
Will you have any experimental tools to probe it?
yeah, I don't think so, because like the coupling is very tiny there. Yeah, so so the idea, so my idea is that since we have this this production at the beginning that we can't get rid of, and we don't know how to control, we don't know how much it is, very, very dependent. This could spoil freezing, the standard freezing. So how can we actually have a freezing model which is self-consistent and doesn't depend on this initial production? And this would be introducing this matter-dominated epoch. Okay, so practically this is what I was discussing: production due to the oscillation of the inflaton, and this gives a bound on how long, how big this delta NR should be. And this looks something like this. And you also get some production of this scalar particle during inflation, which was studied in some other papers up there, and you can recast also that production in terms of this delta NR. And these are independent productions, so this is kind of the motivation that we use to introduce this matter-dominated. So we have lots of production at the beginning, and we need some matter-dominated epoch if we want the freezing to be actually self-consistent mechanism. And these are actually relatively sizable, sizable length of this early matter-dominated epoch, which brought us to think.
Can you just remind me, what was the original definition of delta NR?
Yeah, okay. So is the ratio between the Hubble at the end of inflation? Yeah, and the Hubble at the reheating.
But you are using it seem to be using it as, that's what I thought it was, but you seem to be using it as a proxy for the amount of dark matter that's produced.
That's diluted.
Sorry?
The amount of dark matter that's diluted.
That's diluted. And how do I use it to get as that proxy?
Yeah, so practically, say if there's no matter-dominated epoch,
yes,
then okay, so here we have some production, and then the longer this is, and what longer, I mean, the farther away we put the reheating temperature with respect to the end of inflation, the more dilution we have.
So it's just dilution due to expansion?
Yeah, because we have matter domination instead of radiation domination.
Yes. Okay. Yeah.
And given the bound from Planck, then that becomes a bound on delta NR. So if it's too short, then we still have too much dark matter. So we need a lower length of this delta, of this early matter-dominated epoch to dilute at least enough dark matter.
So you want delta NR to have?
Yeah.
So when there's no time interval, all delta is actually 1.
Yeah.
So
Exactly.
do There is also depend on the coupling strength, how it produces the transfer.
Right.
So
So
we'll land in the next slide.
yeah. So in the case of the inflaton oscillation, that's independent from the coupling, but for the production during inflation, you actually have a dependence on the self-coupling of the scalar field. But like all of this production, I'm not assuming any Lagrangian coupling, so something that I put in by hand between the inflaton and the scalar field. So those production just happen because of gravity. So those will be there no matter what I'm playing with.
Do you have any other cosmological astrophysical limits on this delta and R?
Where you don't want to go until what's that called? Yeah, exactly. So you want to be above. You want your reheating temperature to be above some MED. That's actually the only bound, which is not a strong bound, but yeah.
So can you explain to me, how do you read the top equation? This is an interval that you want to be longer than a time, whereas the right-hand side is the ratio, it's again some ratio of, which is telling me the amount of dark matter produced originally.
Right.
Relative to something or other, which I don't know.
Right. So yeah, I'd say if delta R is more than this, then we violate Planck bound.
So what is the right-hand side? How is it's the right-hand side of it that I don't understand.
Yeah, the right-hand side comes from the production.
And it's the ratio of production of something. So it's the ratio of the amount produced to something else, which I don't know what's normal is because it's dimensionless.
I guess, it's dimensionless, it's like the relic density, right? That would be, if you want, the relic density that you produce, and then you compare it with 0.12 from Planck.
I think the point is the Planck mass here is actually high in physics, so we would have
I think he just
not one of our days.
I think he's hitting the relic density.
So I mentioned general background or something like that.
I would assume so, yeah. Well,
So how is the relic density determined? What determines the relic density?
So the relic density is the ratio between the...
It can't be a ratio, no. It's a relic density, so...
Yeah, but you divide by the critical...
so
by the energy density, the critical energy density.
Omega is squared.
Omega is dimensionless.
Okay, yeah. And omega is the density... or the critical energy density you want to take that closes the universe.
Yeah, you divide by that.
Okay, I'll say you normalize it with respect to the...
Yeah. Yes, yeah.
That's why
I just something was going in there. Yes, exactly. Okay.
Yeah.
All right.
What I'm a little bit confused
Yeah.
about is where did the self-coupling come into play?
Right. So I have to say I had a look more about this part of the production.
Mm-hmm.
This one I took from the papers.
Yeah.
But my understanding was that they were studying the perturbation during inflation in this like in a statistical equilibrium, and that depended on the coupling, the self-coupling of the scalar field. But yeah, I have.
Because that would be the coupling that Danger was asking about. The lambda S would sit in front of S to the 4.
Yeah, that I can only get from the original one. I got that, but it was just the several things like this. I think I understand it now because I would have taken the fourth power of delta in R over R, because that's coming from Stefan Boltzmann.
Yeah.
And that explains that why there's a divided by 4 is taking the fourth root of it.
Yeah.
And the lambda to the minus 3 of, I'm not sure where that's coming from.
Yeah.
Yeah, I have to say, I trusted the papers that they did that. Like I looked at it, but I haven't done the computation. I've done the computation for the
So it's normalized relative to something else,
Yeah.
is what it is,
Yeah.
which I don't know what it's normalized relative to. Because it's divided, the coupling is going to be naturally positive. If there was no production, if the thing never coupled, there should be nothing there, whereas it's going to infinity in this
But
case.
so this lambda is not.
It's the self-coupling.
Is the
It's not-
self-coupling.
It's not the portal coupling.
Is the self-coupling
It's like
of?
of the scalar field
Of the-
to itself.
So lambda is,
show that Lagrangian where you define this value.
he didn't.
He didn't
So
show
Yeah.
the
any-
Lagrangian, you have lambda hs, which was in front of s squared, h squared. Lambda s sits in front of s to the fourth.
Yeah,
Which is
exactly.
self-coupling.
He wrote down the Lagrangian for S, which did not have an S before, did it?
Yeah, exactly.
Yeah. Yeah, I guess I should have wrote yes before too. Right, because so that lambda is not really important for the freezing production. That's why I didn't present it. But yeah, that's the
It seems to
self-coupling.
be essential because it diverges that S goes to zero.
Yeah, for the production during inflation, it does, and that's because of this statistical analysis. So like apparently, if lambda s goes to zero, then you never get a statistical equilibrium of the fluctuation.
Yeah.
So then you cannot describe it through that model. That's why.
Yeah, so, I mean, there's something that's divided here which I don't understand, because you don't get lambda to the minus power without dividing by something in perturbation theory.
Right. Okay, so the point is that since this matter-dominated period seems to be long in order to dilute away the dark matter, then we thought, okay, this means that the reheating temperature is low compared to what we normally have in mind, so the 10 to the 10, 10 to the 15 or whatever. So we thought, okay, what happens with our freezing production when we have low reheating temperatures? And in particular, it's quite interesting to have a look at a different parameter space where that's normally never studied, where the reheating temperature can be lower than the mass of the particle that we want to produce. And if we do that, so we go back to our Higgs portal there, then the freezing production, we are only interested in 2 Higgses annihilating to the dark matter. And now what happens is that the Higgses that have enough energy to produce dark matter are just in the tail of the Boltzmann distribution of the Higgses that are in thermal equilibrium. So practically my production rate is Boltzmann suppressed because of the amount of Higgses that have enough energy to produce my dark matter. That's why we have this exponential suppression there. And if you want, this comes from the Bessel function that we've seen before. When expanded, we get e to the minus x. So the production rate is Boltzmann suppressed, meaning that now the coupling can be much higher than what we had before, because the production rate is very small. Right. Here we consider again an instantaneous reheating to make things simple, meaning that the highest temperature available in the universe is the reheating temperature. Good. So we can have a look at some of the results, keeping in mind what we saw before. And this is what the Higgs portal looks like now. So if you remember, I was saying at the beginning that for freezing Higgs portal, the coupling normally needs to be 10 to the minus 10, so down there. But as you can see here, we're presenting couplings of the order that you would expect for a freeze-out dark matter. So 10 to the minus 2, 10 to the minus 1. And these are the masses of that.
But this is because you're assuming MS is bigger than MX.
Yeah.
The simplest, like, for scalar extensions you use.
Yeah. Right. The gray region is the region that is already excluded by direct action experiments. And these are the reheating temperature that we consider to, as an example, in GeV. So we have 10, 10, 15 until 300 GeVs.
And were the vertical-ish lines?
Yes, the vertical line are lines that give you the correct relative abundance.
Okay, so different colors still give you correct relative abundance. Is the different reheating temperature that tells you where your MS should be, right?
Exactly. So practically all this parameter space is available depending on the reheating temperature. If you choose a reheating temperature, then you can follow this line and you get the correct relative abundance, and then you go down.
And what is the dimension for the reheating temperature? Is that GeV?
GeV.
What is the lower bound on the reheating temperature?
Again, is some MeV.
So MeV. That
Yeah,
low?
I think tens of MeVs.
Okay. Oh, I thought it was.
Sorry, it was-
GeV.
You're saying, but tens of MeV will be sufficient for reheating for all cosmological purposes?
Right, so if you assume instantaneous reheating, then yeah, because you create the thermal bath and then you can go on with the normal thermal history, right? Because nothing we know, like we know nothing of what, like we don't have experimental information of anything at GeV levels, temperature of GeV.
You don't have GeV, yeah? Well, I'm surprised that we have only tens of MeV.
Because
Neutral surface is about 1 MeV.
yeah, exactly. I think that's the bound, like around MeVs because of nucleosynthesis. Yeah.
Wow, so reheating could happen that late.
I'm surprised, yeah. Down to tens of MeV, okay.
Yeah,
So-
I would say fewer.
Can I just
MeVs.
ask a question?
Yeah.
If your reheating temperature is around the electroweak scale, would that affect the electroweak phase transition?
Yeah, for sure. So, I mean, we could also be at lower values than the electroweak phase transition, so it might just not happen during the thermal history in that case.
Yeah, the electroweak phase transition will be way above the 10 MeV.
So it's liquefying this.
Yeah, absolutely. None of those
Yeah.
would be allowed.
Yeah,
But we don't have evidence for them, that's true.
exactly, yeah. I mean, if you are here at 300, then you can still have also electroweak phase transition.
Sure.
And I mean, depending, if you want to go on in baryogenesis, leptogenesis, then you might want to stay to the higher side of this reheating temperature.
There are consistent inflation values that will give the right fluctuation spectrum with such low reheating.
That's a good question. I don't know.
'Cause,
Yeah, I don't know. I mean, I know.
it doesn't allow for a lot of e-folding. Or well, maybe it does, but it's
But the thing is that at the end of the day, you get the low reheating because of this early matter-dominated epoch.
yeah.
So I think that would be just kind of a tuning of the coupling of the inflaton to the standard model. So how late the inflaton decays to the standard model. But I haven't.
Oh, I think warm inflation does that as well. Yeah.
Okay.
So there are models of inflation that allow this fluidity temperatures. I didn't know it was 10 MeV or so.
It's way below the electroweak phase transition as well.
Yeah, and maybe like another thing I have to say is that, so that was the motivation that I presented before to go, like what brought us to study this, but actually what happens here is pretty general, and it doesn't need to be an early matter dominated epoch that brought you to this low reheating temperature. It could be like something else.
And the neutrino fog, I guess you're saying whatever is below that, no way of accessing it experimentally.
Yeah, so this is both to remember that the plan is to get until here at least with next new
What is the
experiment.
green line?
Yeah, the green line is the neutrino fog, meaning when the direct detection experiment we start seeing neutrinos instead of dark matter, and they have plans to go until this line in the future 10 years probably, and then go below, but it's gonna be more complicated than the experiments we have now.
Do you know if it's just more complicated, or do we have no hope of discovering dark matter if we hit the floor?
No, I think you just need more statistics. So what they show is that Yeah, now I don't remember exactly the plot, but they show plots of how to go below the neutrino fog.
Yeah.
It just will take much longer because you have to separate the events between the neutrinos and what possible dark matter can be.
But I haven't heard the term neutrino before, so
That's all right.
it refers to the neutrino background cosmology.
No, not the cosmology.
Neutrino flow is
I think so. I think these are neutrinos coming from the sun.
Well, this is solar.
Yeah.
These are
So
solar
they're
directional.
You can talk about it.
Yeah.
You should be able to sort that out.
Yeah,
Yeah,
So I believe, so I think there are a couple of sources, atmospheric neutrinos and solar neutrinos, then they will be able to see with the dark matter experiments. Like, I don't think we can see the cosmic neutrino background with the...
I was wondering, yeah.
I think that's too small of a signal. Yeah.
I would have guessed that it would be...
I would have thought that any trees would be the problem. Still the trees are directional.
They should be, yeah.
So, I mean, they observed already both solars and atmospheric, but I think in like different type of experiments, I'm not 100% sure. Yeah, but we can also look at this.
Should evolve that far. Is what you're saying, right?
No, I'm saying it's a solar, you can tell.
No, solar I think is easy that directional. But the atmospheric ones,
There are presumably no atmospheric problems in the moon.
Okay. Right. This is what oh no. Okay. Right. This is a good disclaimer. So I'm gonna show you different regimes that we studied, and we can understand them analytically, but the actual computation at the end is done numerically and properly, taking everything into account. So just a disclaimer. Okay, so we're gonna study these 3 dots to understand 3 different regimes that we can encounter. So the first one is the freezing regime, which is you probably can't see very well the green band, but practically you can imagine everything below this line, that's freezing regime. And that's because the production happens just like I described you before with the freezing. You have your Boltzmann equation, and you can neglect that part. And so we saw that if you do the computation numerically, keeping both terms, or if you neglect that, then you actually get the same result. And in this picture, I have the time going in this direction. So this is early time, this is late time. And here we have the half-wall rate in blue. In green, we have the production rate. And in orange, we have the back reaction. So the S's are neglecting back into S's. And as you can see, this is always lower than half-wall rate. So it's never actually active as a process. While this process is active here at the beginning. So we get some production at the beginning, and then this goes below the half rate and it's not active anymore. Right, so that's for the rates. And this is what happens in freezing. Only the forward process is present. The back reaction is always suppressed. But you could ask, okay, but the rate is actually bigger than half-wall. Doesn't that mean we get thermalization? But actually, we don't get it. So we get thermalization when the rates are the same. So the forward and the backward rates are the same. But as you can see, they are different during the whole evolution. So we don't get thermalization. And we can see that also if we plot the yield, so the number density over the entropy density, and you can see that this is the standard freezing yield, if you want ultraviolet freezing yield, and then this is the equilibrium one, and they're not the same. So we are sure we are not in equilibrium. And then we have an intermediate regime there, the blue one, where the back reaction starts to be important. In fact, you can see here, so there are quite a few lines, but if you concentrate on the orange line, which is the back reaction, so the annihilation of the S into the Higgs, And you can see that it is active here at the beginning, as well as the production, which is increased. So now we cannot neglect anymore the back reaction, and we have to do it our computation if you want numerical to get the correct result. And this is the reheating temperature, just to keep in mind the highest temperature, and then we decrease the temperature. So the time goes this way.
The values you've written up there, that's a benchmark point that you're showing the results for?
Yeah, exactly. That's the benchmark point for this plot.
Your lambda HS is very large.
Yeah, yeah.
Do you not run into non-perturbative regimes with which you're not coupling?
Yeah, good question. I guess one should check the next video or the.
Yeah, because lambda HS also contributes to the running of lambda H.
Sorry, can you say that?
Lambda HS contributes positively to the running of the Higgs boson coupling.
Oh.
Sorry, the Higgs quartic coupling.
That is
So with a
okay.
large lambda HS like that,
Okay,
you
okay.
might not stay in the perturbative regime.
Okay, good point. Yeah, we haven't had a look at that, but yeah.
But
that's
if you work with
good.
Oleg, he would know that. So,
Okay. Right. So, but you can still see we are not equilibrating. We get a little bit of damping here because of the back reaction. So you see we reach a maximum, and then there's a bit of damping, but we don't get to the equilibrium part. So still out of equilibrium production. And finally, we enter the freeze-out regime, which is this purple curve, where we get, again, the correct rate abundance, and that's pretty much just what the normal freeze-out predicts. You can see it in the plot on the left that I showed right at the beginning. And here, so we start with, if you want, with this freezing production, but we start with 0 or like almost 0 abundance at the reheating temperature here at 60 GeV, and then we spike up, but then we equilibrate. And you can see that here the two production rates are the same, so we are in equilibrium at that point.
Why is there such a large spike in this case?
Sorry?
Why does it spike up so large? What is it? What is the parameter that's key to forcing it up?
Right. So
you are in this. You've just moved into this next layer of your previous class. So something is critically changed there that drove that up so large.
I assume if you're in freeze out, you start with an initial abundance.
yeah. So
Actually, he
actually,
started with a very low abundance, and it has climbed up rapidly
Yeah.
to in very little change in temperature. And it
so
went up to
yes, I know what you mean. Yeah. So this orange line
Yes.
is the back reaction, and we can see, so it spikes up because the number density of the dark matter spikes up very quickly. Because, so if you have almost 0 dark matter and your coupling is quite large,
It's going
You
to
go to
equilibrate
equilibrium.
up to a large number quite rapidly. It's rapid equilibrium.
Exactly.
Yeah, okay.
and we can see it in the next plot.
Yeah.
You can see this is the yield and bumps up directly at equilibrium, pretty much.
With the parameters you have in the previous transparency, should you be reducing these things in the LHC?
So if the mass of the dark matter is bigger than the mass of the Higgs, you don't see any effect with the Higgs to invisible, so that's fine.
One HS is 2 Higgs to 2 dark matter.
Yeah, but I think
A couple Higgs will produce 2 dark matter particles in the LHC.
So their dark matter is about 1 TeV.
Yeah.
Yeah. So well, you definitely would be producing it at the LHC, but it would be at the very
Very hard to see.
I don't think there's any bounding.
Shouldn't be that hard. Yeah.
No, it is possible, just that the cross section is too low to rule it out.
So if they stay like something's down to the coupling line.
Yeah.
Right. So yeah, here you can see exactly that we get the same behavior as a freeze out at this point. Now the number density is controlled by freeze out, because you equilibrate very fast and then you freeze out at some point there. Right, so that's...
So what would have changed had you had, for instance, that lambda in your, how much would they have changed had you divided lambda, well, was it lambda s, was it lambda hs by 2 in those graphs?
Like in this one or in general?
This one, just
Right, so let me go back to...
Just roughly, what would have...
So like here you can see it pretty much, right?
Yeah.
Like there is, like until you're here, this is you're in the standard freezing case.
So I mean, I'm reading that lambda hs on the right and is on up the axis here.
Yes, so this is lambda hs.
And
this line speaks to what you want, the correct rate of movement.
yeah, okay.
And
So I'm in this regime here now.
Yeah, so if you go,
In that,
so now we're in the purple regime.
yes.
So if you move lambda down, then you need to move
So
the
just
mass.
where so you were very close to, I say, 10 to the minus 1, just a little bit above 10 to the minus 1.
Yeah, I think we were here. Yeah, these are the points. So if you want to stay along the line, if you decrease, then you need to decrease also the mass.
if you want to still get the correct relic density. But
Yeah.
If you want to stay at the correct rate.
Yeah.
Okay. So you would need to decrease the mass as well. So
Yeah.
I see. So that's why the Lara coupling is forced on you to stay at that relic density.
Yeah. While with the freezing is the other way around because of the other way around production. So you increase the coupling and you need to increase the mass to stay along this line. Okay, so just going to my conclusions. So we have early production of dark matter, scalar in this case, that can spoil the assumption for freezing. And we can address this with an early matter-dominated epoch, and this would push the reheating temperature to quite low values. But generally, if you have low reheating temperature, you have a change into your freezing because your production rate can be Boltzmann suppressed when the reheating temperature is lower than the mass of your dark matter. And now the freezing can be targeted by direct detection experiments. And also we can open up parameter space in the lower part here where WIMP anomaly, where no WIMP dark matter model can go. So it can be a future target for direct detection experiments. And moreover, we have now, we can move continuously from a freezing production to a freeze out production. And this is exactly because, so before I was showing you this plot where we have the relic density here, and we have very well separated freezing and freeze out. But when we have low reheating temperature and the parameter space that I discussed, we can push this line to values that are around order 1, and then we can move continuously between freeze out and freeze in, closing this overproduction gap. And yeah, that's it.
you said you were going to say something about spin 3.5.
Yeah, at the end, I didn't put it in because it was already a lot. But so in that case, what we saw, so we didn't need to, so we didn't have a look at the gravitational production of spin 3.5. But even just with freezing, we saw that you need a quite low reheating temperature just for the standard ultraviolet freezing. And that's why then you can also have this Boltzmann suppression in the production. So without going through the early matter-dominated epoch and all of that.
Sorry, for a spin 3.5 you mean Rarita Schwinger, so kind of
Yeah.
So you assume that there are some massive Rarita Schwinger particles?
Yeah, that's what we thought.
I see. But they are Majorana-like, right? Because usually if I think about supergravity, the Rarita Schwinger is neutral with the gravity.
Right. So we didn't assume we are in any SUSY or supergravity.
Oh, well, even if without that framework.
Yeah.
I was wondering, that fermion you assume is neutral, like a Majorana vector.
But it could be also just.
The problem is that there is a problem with the coupling with the electromagnetic field. That's why I'm asking.
Oh yeah. There's no coupling. Yeah, with the magnetic field.
Should be neutral.
Yeah.
That's why.
But it could be also a Dirac particle, right? It doesn't need.
Yeah, no. Yeah, neutral. Yeah, right. It can be also neutral in the sense of Dirac-like.
Yeah.
I see.
That's what we are. Yeah, and there we are studying only this non-normalizable interaction with the standard model.
But then you assume that they condensate. Basically, those fermions like to condensate in principle. They can create, there's some idea that, for instance, some dark matter model come from condensation of some, there is this BC condensation from boson. Or I don't know. You assume that this spin out, create some bound states, or they're just like free.
Yeah, we were considering only free particles. Yeah, not like in condensate. But interesting.
Yeah, because usually also the fermions try to do something, when they're together, that they can interact easily.
Maybe there's some problem with interacting resistring fermions.
Yeah, no, sure.
It's difficult to introduce interactions.
Yeah, but
maybe I have another question. You said in general about dark matter. It's not my field, of course. I remember. So here it seems that you assume that once the dark matter is produced, it's more or less uniform distributed in the universe, right? I mean, as an simplified assumption, right? Because in some galaxy, it seems that there is no dark matter, and that there are this sort of puzzle about, that seems that it's not true that all the galaxies contain dark matter.
Yeah.
It could be a big anisotropy, so distribution of dark matter,
which would be natural if it didn't equilibrate.
Okay, and that's why I'm saying there is any prediction about galaxy level from your non-equilibrium situation, if
So I think in that sense, between freeze in and freeze out, there isn't much difference because you still come from a thermal. So your Higgs is in thermal equilibrium, so you come from a thermal distribution, and then that's transferred to the dark matter. Then for the galaxies without dark matter, I'm not 100% sure, but also I think there was discussion of like capturing the dark matter and then or collision of galaxies and then like the Butler cluster or something.
The Butler cluster. I see.
So I don't know if that could be an explanation.
Okay.
Can I speak here again?